The topic of my PhD and is based on the work that I've been involved in the past 3 years. This talk I will keep at a very high level. So my goal for today is that when you leave this room, you will kind of have a rough idea of what hybrid benchmarking means. So I will really not go technical in this talk. So what does this even mean? Sorry. What do we mean by hybrid benchmarking? This could be a bit controversial because usually by benchmarking, people mean that you actually run a quantum algorithm on the hardware. What we mean by benchmarking is let's find a way to assess the performance of a quantum algorithm without running it on a device. Why so? Because we don't have the devices that we need in order to run industrial relevant problems. We simply don't have enough qubits. So we thought about ways of kind of bypassing this. So the question is, how do you assess the performance of a quantum algorithm without having to run it on an actual device? And the word hybrid stands there because we record classical data and we combine it with very rigorous analytical computations in which we assess how many resources we need for certain quantum algorithms. So basically, what does this mean? So I'm going to present a framework for going beyond asymptotic complexity of quantum algorithms. So usually we have this complexity theory with a big O notation. But what we actually do is to go beyond this big O notation and find all the prefactors that could affect the runtime of our methods. And this work, this framework, was first introduced by Chris Cade et al. And it was called Quantifying Grover Speedups Beyond Asymptotic Analysis. And they applied it for the max K-SAT problem. OK, why is this topic important? And why should we care about this? Well, I'm coming here a bit from an industrial perspective, so to say, in this talk. So people in the real world, they care about having algorithms for combinatorial optimization. And they care about actually doing something useful to them, like to give a solution to their problem, possibly yesterday. So that's why we should care about assessing the performance. So in this talk, I will present 3 topics. The first one is about gate count. So we really went down to the level of counting how many gates a certain algorithm needs in order to solve real-world instances, so the ones with hundreds, thousands of qubits. And for this part, we compared classical to quantum. So we found a classical algorithm that has a 1-1 quantum correspondence. So we could literally compare. Then we have the query count. In this one, we compared only quantum algorithms with quantum algorithms at the level of query. So how many times I have to query a certain algorithm. And at the end, we also did cycle count. Cycle count is also known as layer count. So a layer is form of parallel gates, and we count in how many gates we have per layer. This is something very specific. It's an algorithm that we developed in our research group. And the goal was to solve a very specific combinatorial optimization problem that I will go to at the end of the talk. OK, so is this setting clear for now? OK. So all these 3 topics, they revolve around general linear programming in the standard form. So what we want to do is to solve a system of linear equations in which we want to maximize some function. For example, you want to maximize the profit given certain constraints, and you want to find a solution vector to your specific problem. And there are many applications of linear programming. So on the left side, you will see the mathematical problem, and on the right side, I put an example. So we have max flow. For example, you have pipes in a city. You want to send the water flow, but there are constraints because some pipes are larger, some pipes are smaller, but you want to maximize the flow going through them, or the vertex cover. When you have some intersections, you want to place some security cameras, and you want to make sure that every road is properly monitored. Choosing a group of employees such that they have no conflicting tasks. This is the independent set. And all these three examples are like industry relevant or real world relevant. And the last one is just a fun example where with the something called click problem, you can find a group of researchers where each pair has co-authored a paper together. So there are all sorts of applications. Now, in the first part, I said that I'm going to talk about gate count. All the results that I'm going to show are in this paper with this QR code right here. And this has been a large collaboration, and you will see in the following why. OK. So as I said, for the gate count, we compared a classical algorithm with a quantum algorithm. Why was that possible? It was possible because there were some classical subroutines that we could directly replace by some quantum subroutines. This means that we did a quantum gate count. So we counted how many gates the quantum subroutine needs versus how long does it take to run the classical algorithm for that specific subroutine. So I ran the classical algorithm, and I recorded every step how long it took for a certain part. But for all these parts, I know how many gates I have on the quantum side. So I can find out how fast these gates should be in order to be competitive. Is it clear? Okay. So our working assumptions, they regard fault-tolerant quantum computers. And I will tell you at the end why it simply worked this way. So our set consisted of single qubit gates, 2 qubit gates, and Toffoli gates. So that's what we counted. And each of these gates, they have some implementation cost, but we don't care what's the implementation cost. We just care how many of them there are. And as I said, we assume no errors in the circuit. So all qubits and all gates are logical. So these are our working assumptions. Then we wanted to address 3 questions. Can a quantum algorithm provide a practical speed up over a classical algorithm when the quantum hardware is ready? This was one of our questions. Then what are the gate operation times required in order to be able to actually outperform a classical solver? And are there any instances that are more suitable to be solved on a quantum computer rather than on a classical computer? And starting from these questions, we kind of shaped our goal. And our goal is to assess how a quantum algorithm would perform beyond its asymptotic complexity. So as I said, to find all the prefactors and under benevolent assumptions, meaning that we assume full fault tolerance. And everything is in the context of assessing this performance on real-world instances. And by this, we're just computing the minimum number of gates that the algorithm would require. So it's a lower bound. So in order to do so, we decided to evaluate the simplex algorithm. And what you see here, a feasible region, how these pictures come into play. It's very simple. The region that you see, it's created by putting some linear constraints on the problem. So as I said, we solve systems of linear equations. They have constraints. And these constraints, they define the feasible region. Because all these problems are convex, our optimal solution, we know that we will always find it at the intersection of some edges. And this algorithm, in a very intuitive picture, it works like this. You start with some feasible solution, and you want to find the optimal solution. In order to find the optimal solution, you need to move either to the left or to the right on this polytope. And now there are many rules which tell you, OK, do I go left or right? You can pick your favorite rule. For example, I picked the one that goes to the steepest slope in this case. And you just go, and at some point you find the optimal solution. You also have to check optimality, and so on and so forth. But that's the rough picture. You start from a solution, you go on the edges, and at some point you find the optimal solution. Now, on a bit of technical level, what does this mean? We started with some systems of linear equations with inequality constraints. The problem transforms them into equality constraints. This is how you get the polytope. Then you set up some sort of tableau. Then in order to pivot, in your matrix, you need to find the pivoting column and the pivoting row. Then you pivot, and then you update. But let's do this on an example just to see what this means. So we have some profit function here. And we want to maximize this profit function. But our system has some inequality constraints. As I said, the first step is to write the problem in the standard form, which means that we transform everything into equality constraints by introducing some additional variables. And these variables are also larger than 0. And then we set up what we call the simplex tableau, where we simply put the coefficients into some rows and columns. So yeah, this is the 2. Here comes the 1. There is no z in the first equation, but there is a nu coming from here, and so on and so forth. And in the last one, we just put the function that we want to maximize. So we put those coefficients. And now the rule goes as follows to find the pivoting. So this is the tableau with which we started. And as I said, you can pick at random a column, or you can pick it according to some rule. Some people go for the minimum value in this column, but in this example, we pick this, or the person who made up this example, they pick up the first column. And then the goal is to have here your solution vector. So as long as I manage to get to heaven 1 with my x, then I found the solution to this problem. But more specifically, how does this go? So, well, the first step is to get rid of the 2 here. So every time the algorithm takes this value 2 and just divides everything here by 2. So that's how I get to this step. But then the goal is to have zeros. So after another step, I can get a value for x. But this doesn't mean that I found my solution, because I don't yet have the values for y and z. But this is just how you identify the pivoting column. Then the pivoting row is just to do all these linear tricks. Then you update. And sorry, it's stuck. OK. And 9 steps later, you actually find your solution just by keep on doing this trick over and over again. And on the right-hand side, you found the values of x, y, and z, together with the maximum profit that you could obtain. So this is on the classical side. Nannicini proposed these fast quantum subroutines for the simplex method, which means that the steps that we see here, they are replaced by quantum subroutines. And this is a direct one-on-one correspondence. So we find the column, we find the row, but of course we need to check if they are optimal and if the problem is not unbounded, because you don't want to divide something by 0. And this is the general setup for simplex. So you have the classical side, you have the quantum side, and there is a one-on-one correspondence between the subroutines. Is it OK by now? OK. OK, but this doesn't look that bad, right? Like we have this one-on-one nice correspondence, and yeah. In theory, it's actually not that bad, because simplex, it's an exponential time algorithm. But if I look only at the pricing step, then I can look in the big O notation, and I can see, OK, what's the complexity of this algorithm? And let me break it down. So this stands for the sparsity of the matrix. So the maximum sparsity, the number of non-zero entries in any row or column. Then M and the number of constraints and the number of variables. On the quantum side, you also care about something called condition number and error. But the idea is that even in this case, when you look at the asymptotic complexity, it seems like the quantum part would just do a bit better. But if you dive even deeper in this algorithm, all these nice subroutines that have the one-on-one correspondence, they are made up of other quantum subroutines. And each one of them is a mixture of more than one of the ones that I just wrote here. So they are all a combination of quantum search or amplitude estimation or some LCU or some amplitude amplification and so on and so forth. But when we dive even deeper, it's not enough to know that, okay, there are quantum subroutines. You need to know what's behind those quantum subroutines. And as I said, I don't want to go technical, but I've put these two subroutines here just for some sort of an overview to know what it means to go beyond asymptotic complexity. So normally people would say, yeah, Grover gives you a square root speedup. Yeah, that's correct, but how many times do you have to call Grover? And you can actually compute an expectation value of how many times you have to call Grover. And that looks something of that sort. Also, this is a quantum linear solver based on Fourier polynomials. And the idea is that every time when I go from one point to the other, I have to solve the problem, meaning that I have to invert the matrix. And for that, one can use a quantum linear solver because they approximate the inverse of a matrix. And they also have good asymptotic complexities. But when you go to the gate level, things can get a bit messy. And yeah, the reason why I added these two subroutines is because they are part of all the other 4 subroutines that you saw before in the simplex method. So when one dives deep, yeah, things get complicated. I think that's the point. And yeah, okay. We have all these lower bounds on the number of gates. And then we wanted to compare, okay, can we do actually better than the classical solver or not? Because we know from the complexity theory that we should do better, but let's see what happens in practice. In practice, the situation is not so pink, so to say. The current speed gate record for an isolated operation is 10 to the minus 9. And the simplex is just very fast. So for every iteration of the simplex algorithm, we had the number of gates, and then we saw, okay, but no matter if we give hard or easy instances, these times are quite unrealistic. So 10 to the minus 16 or 10 to the minus 19 for a single gate operation. And now, why is this relevant? This is relevant also on a classical level, so to say. First of all, I don't think that it's possible to have gates that run so fast. I don't think that you can actually physically construct them. I think there are some limitations. But also, it's important to do this kind of analysis because this holds also on a classical level. When you compare classical with classical algorithms, there are some of them which have bad asymptotic complexities and perform very well in practice, like simplex. And then you have quantum algorithms, classical algorithms that perform very well on the complexity theory, but very bad in practice. So this was part of the motivation to look at this comparison. And then we said, okay, let's assume we allow for these very fast gates. Let's see what happens and if we can actually obtain a speed up or not for the instances. And it's not always true. It depends how fast you allow the gates to be. And by this, you simply cannot do it. But this is a bit of a negative result, but the method still holds. Like if you take this method and apply it for another classical versus quantum algorithm where there is a one-on-one correspondence, maybe you get some positive result. But this is just how it is. So we kind of answered these questions. Can a quantum algorithm provide a practical speedup? Well, for simplex, no, but maybe for others, one has to check. What are the quantum gate operation times? Well, they are highly unrealistic, like 10 to the minus 20? And are there instances that are easier to solve on a quantum computer? Well, no, because like it's still in this regime of unrealistic gate times. So this was the first part, and I will move now to the second part. Yes, so in the second part, we wanted to compare functional quantum linear solvers to see which one performs better a bit if we go beyond this asymptotic regime again. So we counted queries. So how many times do I have to query a certain quantum algorithm? And again, we had these full fault tolerance assumptions. So yes, there are no errors in the circuit, qubits are perfect, we can implement any gates. And furthermore, we have to make a few other assumptions that all algorithms have access to the exactly same oracles and that this access is sparse. So all algorithms, so all linear solvers in this case, they call exactly the same oracles, and these oracles, they access the entries in the matrix. And the questions that we wanted to answer here, yes, if there are any parameter regimes or special cases where quantum algorithms could do better than classical ones, and which quantum algorithm shows the best promise in a given parameter regime. So as before, we had a goal, so to assess how quantum linear solvers would perform beyond their asymptotic scaling under benevolent assumptions and when applied to real-world data sets. So as before, we consider a system of linear equations where it's very important that A is sparse and well-conditioned, which means that, so by this I mean that the number of non-zero entries is logarithmic in the problem size, and also that the condition number, it's as well logarithmic in the problem size. And yes, when you apply these two conditions on real-world data sets, you realize that there are not so many problems that you can look at. But let's see. So we did the same trick again, but instead of going up to the gate count, we did the query count. And this is how our equations look like. I will not explain how we exactly got to them, but two parts were very important, this NQAA and this big Q here. So we counted the quantum amplification overhead that came from all the algorithms, and two of the methods, they are heavily dependent on the Hamiltonian simulation method that you are picking. So all these linear solvers, they could improve if you can find a bit of a better Hamiltonian simulation method. But to my knowledge, the current state of the art is this qubitization method. So as you also see here, we need to compute this overhead for all the methods. And by this, we also kind of needed to approximate the success probabilities. So we had to be very rigorous as well there. But for this one, I want to mostly focus on the results. So we compared 4 functional linear solvers, HHL, that is widely known in literature, and it was the first quantum linear solver. Then we looked at the quantum linear solver based on Fourier polynomials, then the one on Chebyshev, and in the end, we looked at QLS, QSVT. In this first data set that you are seeing here, we randomly created these instances, and we just made sure that they fulfill all the conditions, all the ideal conditions for quantum linear solvers. And we saw that, unfortunately, HHL is not really a viable option because you just need to query it like 10 to the 16 times, while for the other methods, you had to query them like 10 to the 10, 10 to the 4 times. So, yeah. So therefore, we discarded it in the other results, and we compared just the other 3 of them. And this one, we looked back at simplex, but this time for the simplex, we picked only the well-conditioned and sparse data sets. And we noticed that the quantum linear solvers based on Chebyshev polynomials are way more promising than the Fourier one, but maybe Fourier is easier to implement, maybe it makes sense in some context that I don't know. And in the end, we also looked at Poisson equations, but the conclusion was the same. With the exception that in this case, we didn't allow for, we wanted to have well-conditioned matrices, but they were not well-conditioned, but still, I would say that the methods perform quite well. So the conclusion is basically, if you want to use a quantum linear solver, try to orient yourself towards the ones based on Chebyshev polynomials. And one, for example, for the simplex that you saw before, we use the Fourier method, but now one can also go back in time and maybe try one of the other methods and see at the gate level if it will do better or not. I don't think so, because there are many more overheads there, but one can try. Okay, so we kind of answered the second question, that the quantum linear solvers based on Chebyshev polynomials show the best performance. And for the first question is what I said, like maybe one should go back into simplex and then you can compare on a gate level and then you can compare with a classical algorithm. Because in this context, it's not fair to compare directly with a linear solver, since we just counted query calls to specific oracles that access the entries in the matrix. So the goal here was to have a method to just pick your favorite linear solver, and one can also do the same tricks. Like find all the prefactors, use real-world data sets, and see what happens. Third part is about an algorithm that we developed and the way we benchmarked it. And this algorithm and the benchmarking method, they are tailored for this very specific problem called 0-1 knapsack. So again, we assume that everything is ideal. And in this case, we counted, my pen is no longer working. We counted processor cycles. So classically, you always count a processor cycle, and that's what we also did here to have a one, what we call meaningful comparison. So let's see what is this knapsack problem. So basically, you have a bag, and you want to pack items, but this bag has a certain capacity that you have to obey, and you also want to maximize the value that the things that you pack will bring to you. And so we have something to maximize. We have some capacity constraints. Maybe it's still not working. And the idea is that this problem is NP hard, but in practice is rather to solve. So you see, again, we have this duality, like complexity theory, like tells us that these problems are NP hard, but people came up with solvers, and these solvers in practice most of the time manage to kind of easily solve these problems. And the classical state of the art here is a method called combo, or an algorithm. Okay, so let's look at an example. So we have some bag of capacity 3, and we have here 3 items with their profits and weights. So item 1 has a profit of 4 and the weight of 3. Item 2 has a profit of 2 and the weight of 2, and item 3 has a profit of 3 and the weight of 1. And this is like our exclusion-inclusion tree. We begin by not including any item in our bag. And then we can see what happens. So if we include the first item, we already are at the capacity of our bag because the weight is 3 and this brings a profit of 4. So I can no longer include the items 2 and 3. If I don't include the item 1, then I can include items 2 and item 3 and still be within my capacity constraints. But now the question is, okay, which path is better? Well, the better one, or the optimal one, is the one that maximizes the profit. And in this case, is the solution here, because we have a profit of 4 versus a profit of 3. Now, this was the starting idea. Then we moved on to some quantum version of it. So here we are working with registers. The first register records the path. The path is what you saw in the previous example, is 0, 0, 0, 1, 0, 0, so on and so forth. And this corresponds with including item 1. Then the second register records our capacity, so how much we can put, and the third one records our profit. And in our case, the algorithm, we named it quantum tree generator in analogy with the tree that you saw before. Yeah, and in this case, we can explore this whole tree in superposition. And when we do so, we keep track of these cost and profit registers. So we decrease the cost register with every item that we add, and we increase the profit register. And maybe from this example, it's more obvious that here it's a larger profit than here. So yeah, basically we explore a tree in superposition with QTG. And this is done by using 3-layer unitaries. The first one uses RY gates in order to create the superposition tree. Then we have some ways of adding the profit and subtracting the capacity. But we also want to amplify the probability of finding the good solution. So we have them in superposition, but when we explore the tree, we want to amplify the probability of finding the optimal solution. And this is another visual example that we made. So here you consider you have 4 items. You again start from 0, 0, 0, 0. The QTG creates the hypercube, or the tree, where the green points are the feasible solutions, and the red ones are the solutions that are simply excluded, because they maybe don't fit with the capacity constraints. And then when you move from one iteration to the other iteration, then you increase the probability of finding a good state. And you do this process a few times, and at some point you arrive at the wanted solution, not always with 100% probability, but with a good enough probability. So this is just a very high-level overview how this is working. And now, what happens when we use the QTG? So first, we looked at memory requirements, because people in general start using the 0-1 abstract by using dynamical programming, and that's very memory heavy. So we started looking at the memory first, but dynamical programming was not actually competitive with Combo or with other solvers, so we dropped it at the end. And as I said, Combo, it's like the current champion for the classical solvers, but for us, here is the memory that QTG requires, and it's quite constant across all problem sizes. And by size, I mean the number of qubits, and also by different hardnesses. So that G tells us how hard a certain problem is. And we compare with a few methods. So we also benchmarked another quantum method called quantum branch and bound, but we also looked at the memory requirements for other solvers like CPSAT, Combo, and iPistons here for Gurobi. And then we said, okay, memory is quite good, but can we have a speed up, or does this method brings us anything more into that direction? And the answer is yes, but for very hard problems. So what you see here, we did, again, the same comparison where we used Combo. We also benchmarked the quantum branch and bound and 2 more methods. I can explain them later. But the idea is that when you go to harder and harder problems, then the QTG can actually provide a speed up over the classical methods. And yes, as a summary, what I wanted to talk about here is just a framework in which you can benchmark algorithms without having to actually run them on a device, and that a good asymptotic complexity doesn't result in a good practical performance, and that QTG has the potential for speed up over classical methods, at least for the 0-1 knapsack. And there are also some works in this direction, both for QTG and also for the first 2 hybrid benchmarking techniques. But of course, there are some open questions like, Can we use another QLS for simplex? Can QTG be used for other problems? Can it be generalized? Or what happens if we add errors to QTG? So that's all.